Alright, another in my series of explorations of vintage Heathkit test equipment. As usual, I'm going to start with Chuck Penson's excellent book, Heathkit Test Equipment Products. And let's go right to the meters chapter, which covers both frequency counters and multimeters. These are all frequency counters. The first digital multimeter produced by Heathkit was the IM-2320 in 1972. I have one of those. It does not work properly. It's unrestorable as far as I've been able to determine. Too many proprietary parts are shot on it and ICs that are just unobtainium. But it does power up and make a display at least, and I put that in a previous video. Then Heathkit had a series of lower end digital multimeters, starting with the IM-2320, following it with the IM-2320, which in turn was replaced by the IM-2310, dating from the 1972 to 1975 range, then the 75 to 76, and then the 76 to 82. Around the same time, Heathkit had some higher end meters, which were 3.5 digit meters. The IM-2320 was a manually ranged meter using a Panaplex display, the only one of their voltmeters that use that technology, and I have a separate video on this unit. And then it wasn't replaced by, but it was supplemented by the IM-2320, which I also have a video on. This one used an LED display, and it was also auto-ranging. A very nice meter, really. And I have a video on that one. That one went up until 1982. In 1979, really the same time period as the 2212, and made up until they exited the kit business, is the IM-2320, a handheld digital multimeter with an LCD display, and I have a video on that. It's actually a very nice meter. Then, to replace the medium and higher end meters, Heathkit had the IM-2260, which was an LED DMM. I have one of these, but I have not yet done a video on it. And then at the same time they introduced that, they had an LCD display version of the same thing, the IM-2262. I also have one, and we'll be doing a video on it. And at the same time, they introduced the top of the line of this set of three, the IM-2264, which is pretty much the same as the 2262, but they've also added a small analog meter to allow viewing trends in the signals and dynamic signal swings that you couldn't get with the purely digital meters. And again, these models petered out at different times. The 2262 ended in 83, and the 2260, the basic LED model, they continued and they sold it all the way up to the bitter end in 1991. And the 2264 ended in between those two. It didn't make it all the way to the end. Apparently this was their most popular model because that's the one they kept making. When they discontinued the 2215, they replaced it with the 2220, the subject of this video. Oh, I forgot to mention that I will also be doing a video on my 2264 that I have I'll probably make one video covering all three of those models, but that's for the future. The IM-2320 is their last model, and they continued it nearly to the end. It was discontinued before the company exited the kit business, but not by much. It's very similar in functionality to the 2215, but they went with the more conventional big rotary selector switch instead of side-operated buttons. It uses the same internal circuitry for much of its functionality between these two models, but they did add some additional ranges, and they added the ability to test capacitors and transistors, and it also has a continuity function with a beeper that the 2215 did not have. So let's look a little closer at what the book says about the 2320. So again, introduced in 1987, discontinued in 1990, cost $70 at that time. As I already mentioned, it measures capacitance and transistor HFE, or gain, current gain. It features auto polarity, auto zero, and a low battery indication. AC and DC voltage ranges are 200 millivolts and 2 volts, 20 volts, 200 volts, and 1000 volts. Although on the AC, for AC volts, it only goes up to 750 volts. Resolution 100 millivolts on those ranges. Accuracy plus or minus 1.25% of the reading plus 4 digits. It has DC amps range, 200 microamps, 20 milliamps, 200 milliamps, and 10 amps. So the ranges aren't purely in orders of magnitude. They obviously picked ones that they thought were most likely to be useful. And an AC amps range that's just the same, but it leaves off the 200 microamps at the bottom. Resistance goes from a 200 ohm range and then up in decades: 2K, 20K, 200K, and 2 meg and 20 meg. Capacitance in 1, 2, 3, 4, 5 ranges, from 2 nanofarads, 20 nanofarads, 200 nanofarads, 2 microfarads, which would be 2000 nanofarads, and 20 microfarads. Runs on one 9-volt battery, discontinued in 1990 and not replaced with another model. So, with the preview out of the way, let's dive into the real thing. Okay, there's the beauty shot. Alright, let's take a look at the markings on the front panel. We have our volts and ohms jack, our common, our milliamp jack, and our 10 amp jack. So volts and ohms regardless of AC or DC volts, and all the continuity functions are done with the red lead here. The common always goes to the common, that's the black lead. Then you could move the red lead over to the milliamp jack if you're measuring AC or DC milliamps, or over to here if you're measuring up into the 10 amp range of current. It does caution that when you're in milliamp mode that it's 200 milliamps maximum, and that you should not have more than 500 volts between the common terminal and earth ground, and that you really should not have more than 10 amps maximum between the 10 amp and the, or not between, but through from the 10 amp jack to the common. That is its maximum rating. And then over here for volts, if it's DC volts, you can go up to 1000 volts. If it's AC, it should be 750 volts maximum. So let's look at the top here. So we have our power on and off switch. There are 3 pins in the female header for minus on the capacitor, and 3 for the positive of the capacitor. It's a little hard to see there, but there are 3 holes down there. They're a little bit misaligned. They're up here a little bit, but you can still put leads through. And then for the transistors, they're better aligned with the slots in the front. So you can plug in a NPN transistor here or a PNP transistor here. In each case, it's emitter base collector pin arrangement. So those functions are done here. Going to DC volts, the lowest range is 200 millivolts full scale. In reality, because this is a 3.5 digit multimeter, when they say 200, they really mean 199. Then there's a 2 volt range, a 20 volt range, 200 volt range, and the 1000 volt range. If we go to AC volts, it's 200 millivolts, 220, 200, and 750. So these are like complementary. You don't, it's a little bit counterintuitive. If you keep turning the switch past the DC volts, you don't end up in the lowest AC volt range, and that may make sense. If you're bopping back and forth, you don't want to necessarily go from the highest voltage range on DC to the lowest voltage range on AC. So that makes some sort of sense. This is not an auto-ranging meter, so following good common practice, you start with the highest range and then check to see what the display is and keep switching it to lower ranges until you get a good reading, instead of just plugging it in like modern meters on any old range. Well, you don't usually even have a selector for range, and just let it auto range, but this does not have that. It's too early. For capacitors, we have a 2 nanofarad full scale, 20 nanofarad, 200 nanofarad, 2 microfarad, and 20 microfarad. So this does not measure really big capacitors, but it's down there, 2 nanofarad. You can read some picofarad values and so on. It's a nice midland range. In ohms, the lowest one is for testing diodes or as a continuity checker as designated by this little musical note symbol. And then you've got 200 ohms, 2 kilo ohms, 20K, 200K, 2 meg, and 20 meg, which is not a bad selection of ranges. You've got 1 position for testing the HFE or gain of the transistors up here. And in DC amps, you've got a 200 microamp range, and then the 20 milliamp range and a 200 milliamp range. You run out of gas pretty quickly on the amps here. If you're higher than 200 milliamps, it's not like there's a 2 amp range above that. You have to go straight to the 10 amp range, and for that you have to go back to this middle position. But of course, to do that, you're moving the jack over to from here to here. And then on the AC amps, there's only 2 ranges: a 200 milliamp range, or sorry, a 20 milliamp range, or 10 amps depending on the jack, and a 200. So it does not have the microamp range. And let's see, I already covered the capacitors, so that's all of the functions on the selector switch. Okay, here's the inside of the meter. It's on 2 circuit boards, the main circuit board and the front circuit board. Front circuit board is primarily just access to the switch contacts, and then there are some jumper wires that go down, and also the battery gets wired through the front board. It's kind of hard to see, but you can see the nylon housing there. That's not the actual switch. That just provides the detents. It's basically a big plastic ring that's screwed into the circuit board in a couple places. And it has a interior, the interior face of it has notches into which a spring clicks, and that provides the detent for the rotary switch. The actual switch contacts are made on foils on the circuit board, on the back side of the front board and the front side of the back board. And there's a little contact carriage that is controlled by the knob here, which rotates within that ring and makes various connections. You can kind of see it through the board there. You can see some of the rings of contacts in there. Anyway, so what we have here is the 4 terminal posts and the fuse that's only used on the lower current or the milliamp ranges. It's not used for voltage or ohms or anything. It's just for the lower current ranges. And then there are a couple of socket headers which are used for the capacitor and transistor features of this meter, where you can plug their leads into those. There's the little piezoelectric transducer that acts as the beeper in the continuity mode. There's the power switch, and there are a few components on the front boards beside the switch, but not that much circuitry on the front board. Most of the circuitry is arranged around the outside of the main board. And there is a logic chip there, the 4070, which is used to control the decimal points on the LCD display. And unfortunately, the LCD display here has a little bit of dust that got inside of it. And I was going to pop it apart, but the contact strips that are making contact with the rear of the LCD often don't survive that operation. And also, I have to spring the plastic out. And with something this old, often those will break in the process. This is working really well, so I don't want to risk busting it. So I'm leaving that little bit of dust in there alone. And then the main IC, you can see it back in there, is the monolithic voltmeter and display driver chip. So that's really the bulk of it. Oh, this wire there is the the shunt wire for the 10 amp mode. And I think that this is another precision shunt resistor there, for probably used in the milliamp modes. I haven't traced it out to see what that's in. That could also be one of the other resistor dividers, for example, for the volt ranges, which is actually probably more likely. The components closest to the main chip are its support components. And really, other than some precision resistors and a couple transistors and a few other things, there's not really that much circuitry in here. The plastic case is just a front and a rear with a little door for access to the battery and fuse. And it's fairly typical for, you know, commercial meters of this era to be built this way. There's the circuit board stack dropped into the front of the case. Have to make sure that the power switch engages. The little cosmetic outer part needs to align with the physical switch. It won't drop in there unless it is aligned. Pretty tight fit, not a lot of extra room in here. There's the battery compartment and its little foam pad, and then there are two clips into which you can put spare fuses. It's a little 1/4 amp fast blow fuse there, and it's an interesting type. It's designed to be accessed from one end instead of pushed down straight in. So this side's got a roof on it, so to speak, with a spring. So you push the end of the fuse into that, and then drop the right side into the right clip, which has a couple retainers. Unless you push the fuse a little bit to the right, it won't disengage the retainers on the right clip. Then there's a bent piece of cardboard with a metallized face on it, which is used as a shield, and it slips down and fits into some little grooves and between some plastic fingers on the front of the case. Oops, it's shifted a little bit. There we go. So that it gives access to the various trim pots. And then there's one screw that goes in here to tie that into the circuit ground. Like that. And then the back of the case is held on with 3 screws that tap into posts on the front of the case. Like that. And you're left with the fuse in its clip, as I've already described, a place for a couple of spare fuses, and the location for the battery. Now, this just takes a regular 9-volt alkaline battery. It doesn't work with rechargeable ones, or at least you might get it to work with a rechargeable 9-volt battery if you can get your hands on one, but the circuitry isn't set up to charge that battery once it's in there. And the battery goes in right side first and then slips down in there like that. So it's fairly tight. And then finally this little part clips on like that. And you have a fairly handsome looking case. Certainly in line with other products of the same era. Now the case has a kickstand on the back that holds it at a decent angle for viewing. And there's the model and series number. It's a little rubbed out, but it looks like it's 01, then a space 69120. And of course it has the IM-2320 on there. And it does mention that it takes a 1/4 amp. Doesn't say slow blow or fast blow, but it should be a fast blow. 250 volt rated fuse, 9-volt battery. Okay, let's start the demonstration with the DC volts. I'm not going to bother going down to the super low range. I'm just going to connect up my bench power supply to the test leads. And I've got a residual 0.004 volts hanging out there, with presumably 0 volts provided by the power supply. So I'm going to go up to 1 volt, and we're pretty close, 0.997. And we're over range because we're on the 2 volt range, so it just shows a 1 point for over range. So we select up to the 20 volt range, and I've got 1.99. Again, that's well within tolerance. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, and I'm overranged because I'm in the 20 volt range. Select to 200 volt range, and now I'm showing 21 volts for 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, and that's it. The power supply does not go any higher. So I'm just bring it back down. Take it down to about 8 or 7 volts. And of course that works perfectly well on the 200 volt range. If you don't care about more than 1 decimal point of accuracy, you could just leave it on the 200 volt range for all your measurements. You know, so that's 1 volt. Really good performance on the DC volts range. For AC volts, I'm just going to test it at a higher voltage range. So I've got it on the 200 volt AC range. I have the meter connected through my benchtop AC access box. I have a separate YouTube video on that. And that in turn is plugged into my Variac. So I'm going to turn on the switch here. There's not any voltage applied at the moment, so the neon light does not come on. But let's see here. This should be in the vicinity of 50 volts, according to the Variac, and we're really much right there. This is more precise than the Variac is for sure. That should be around 100. That should be about 120, and it is. Very good. Okay, now I'm going to test DC amps in the form of 20 milliamp range. Nice mid-range selection. And again, the circuitry on here is identical for AC and DC, with the exception of the AC to DC converter circuit, which we've already tested and proven working on the AC and DC volts ranges. So the amps ranges are again identical, except for that circuit, which has already been proven. So I'm not going to bother demonstrating the AC amps, but for DC amps, I have my leads plugged into common, and the milliamp range, I have those wired in series with a 4 to 20 milliamp current loop tester or transmitter, and my power supply on 24 volts DC, which when I turn it on, I'll get an indication here that the loop is okay, and it is currently selected to mid-range, which should be halfway between 4 milliamps and 20 milliamps, in other words 12 milliamps. And what do I have? 12 milliamps. I can throw this switch, which will take it to minimum range, or 4 milliamps. There we are. Go back to the 12. I can throw this other switch and take it up to 20 milliamps. And it's over range because this is really 1.99 range, so I have to go up to the 200 milliamp range, and it's showing a nice clean 20 milliamps. Go back to that. I've got 12 milliamps again, and I can just vary it using the knob. So that's working perfectly. Now this meter, as I bought it on eBay, did not come with a set of test leads, or rather it came with some sort of cobbled together fragments of busted up old test leads that were stuck together with glue and shrink tubing. And while basically functional. They were not anything I would keep with the meter, and I'm sure they weren't the original ones anyway. It was just something the seller must have had on hand, or maybe they came when he bought it in an estate sale or wherever he got it. Anyway, these are the modern kind here that are the safety style, and they are compatible with this meter. So there are no contacts exposed there, but once you push them in, they do make contact with the barrels in there. By the way, I'm really liking these probes I bought from Amazon. They seem to be quite good quality. The cords are advertised as being silicone rubber, and or silicone rubber, which I think they are from the feel of it. Nice and loose. They're not kinky or stiff. So they're a better quality of that. Not as good as like the professional Pomona leads that, you know, maybe come with like a nice fluke meter or something. These are still better than these, but these are pretty good. And these are modular, so you can, well, they're kind of stiff, but you can, you know, unplug the test probe from the lead, and again, it's a safety connection on the lead, so you can't come in contact with it with your finger. You have to push it into a open barrel connector to make contact. And then it comes with a set of alligator clips, which again are the safety type. So if you want alligator clips on your test leads instead of probes, you can do that. And it also comes with a set of mini clips that plug in and give you the tiny little clip. So pretty versatile. Okay, let's test the various resistance related functions. First off, I have the meter in the diode test and continuity mode. It's the same mode, it just gets used a little differently. So I have a pair of leads out here. So I just have a 1N4004 typical silicon diode just stuck in here to hold it, and one of the test leads from the meter is connected to there, and the other lead is here. Now if I touch the cathode, I can get a value, in this case about 0.6. If I reverse those, I get nothing. So that's the diode test mode. If you get infinity, then the diode is reverse biased and it is not conducting. If you forward bias the diode, then you get a reading like this. Continuing on in the same function, just as a continuity tester, I'm just going to touch the test lead up here. We'll see what the display and the buzzer or beeper does. So it shows a reading of approximately 0, so no resistance, and we get the nice loud beeper. Now if I connect this up to my resistance decade box, let's start cranking up the resistance. That's 1 ohm. Up to 9 ohms, it doesn't see any difference. Let's go to 10 ohms, 20, 30, 40, 50, 60, 70, 80. At 80 ohms it stops saying continuity, although it keeps reading the resistance value. So continuity according to this meter is anything below approximately 80 ohms. So right now the decade resistance box is set to all zeros, and I'm in the 200 ohm range, so I can happily go up. That should be 6 ohms. It's showing 6.2. There's about a 0.1, 0.2 quiescent ohms on this. Just the internal wiring and the test leads add up to that much. So it's always going to be reading a little high just because of that quiescent resistance. Okay, that gets me up to 9 ohms, and I'm going on to the 10 range. 10, let's just go up to 50, 80. It's reading pretty well. It's well within tolerance. Now I can go to 100, and that's 200, but I'm overranged. So I switch to the 2K range, and I've got 0.2 K, or 200 ohms. 3, 4, 5, 6, 7, etc. Let's go to 352 ohms, and we're reading 353 ohms, or 0.353 K. And it's giving it in K because I'm in the 2K range. Let's take all that stuff down, and let's crank her up to 1K on the 1K range here. I've got 1K in a small fraction. Basically 1K and 6 ohms quiescent. If I go to the 2K position, it's going to overrange. So I go to the 20K here, and I'm 2K here, so it's reading a nice even 2K. Now I can bring in like a 4, that's 400 ohms, 2.4K, and I'll bring in a 7 down here, so 2.47K. Now let's go to 3K, 6K, it's all very close, 9K. Let's go to 10K, and that gives us 10K, but if I go to 20, of course it's going to overrange. So I go to the 200K, and I've got a nice 20K, and I can crank her up. That should be 60K, reading 59.9. Take it back down. Let's go up to 100K, and I get a nice reading there. If I go to 200 here, we're going to overrange. It's actually right on the hairy edge. It's reading slightly low, a little bit of tolerance in this, so it actually doesn't overrange, but it's right on the hairy edge of doing so. If I go to 300K here, it definitely overranges. I have to go to the 2 meg range, and I'm reading really close to 300K there. 600K, 2, 6. So again, very close. More likely to be tolerances in the resistor box than in the meter itself. Crank everything back to 0, and I've got a nice 0 here. So the ohms range and the continuity and diode test modes are all working perfectly. Let's test out the capacitance ranges. I have a few pre-measured capacitors from my junk box. I've got the meter set to the 200 or the 2 nanofarad range right at the moment, and I'm going to plug in this capacitor, which let's pretend I don't know what its value is, and it plugs in real easily like that, and it's reading 1.112 nanofarads. Well, this happens to be a 0.001 microfarad capacitor, which measures on a professional meter as 1,000 189 picofarads, which is 1.09 nanofarads. So, you know, on here we're getting 1.11 nanofarads instead of 1.09, so it's off by 2 of the least significant digit. That's not bad at all. Let's plug in this guy. Well, it overranges, so I have to select up to 20 nanofarads. And there we go. So it's sitting there around 8 point. It's creeping up slowly. I think this capacitor is well past its sell-by date. If it's not stable and doesn't just center in like it should, notice how the other one just went to a value and held it. Here it keeps creeping. That's a breakdown in the structure of the capacitor. These are quite old capacitors. It's hovering around 9.3, still creeping up a little bit. So that would be 9.3 nanofarads. This is a capacitor marked 103, which is a 10 nanofarad capacitor. And it was tested at 10.3 nanofarads on a professional meter. And it's reading, you know, well, a little bit low, but it's in the ballpark, so still a useful measurement. Now let's take this little guy here. Even though this is a small capacitor, it may not be a small value, and sure enough it's overranged. I'm going to select up to the 200 nanofarad range and see if I get something. Okay, it's hovering around 93.5, so about 93.5 nanofarads. That capacitor is marked 104, which is a 100 nanofarad part nominally, and it measured on my professional meter at 93 nanofarads. And here we are. And this is a very new part. It's, you know, only made within the last couple of years, so it's a much more reliable one than these old parts I probably had for decades. But that's not bad at all. Now let's try this electrolytic capacitor. And it is polarity sensitive. I have to make sure I have the polarity correct. And it's overranged, so I'll select up. Let's try this one. Now we're getting a reading. So on the 20 microfarad range now we're getting a 10.37 reading. This is nominally a 10 microfarad capacitor. It checked out as such pretty close to what it should be, and it's reading 10.34 here, so again very close to the value I got with a more professional capacitance meter. So this is actually for a little throwaway function they just added on here for a minimum of extra components and cost, and within the fairly narrow range of capacitance that this can handle. And it doesn't go into the really tiny values, and it can't go very large, but within what it's got, it's not too bad, not too shabby. Okay, the last function is the HFE mode. And I'm going to test out a PNP and an NPN. I don't have any idea what the HFE on this transistor is, so I'm going to pull my peak transistor tester, and it's recognizing it as an NPN transistor, a silicon NPN transistor, with the red emitter, the green base, and the blue collector. So this is an emitter base collector pinout. And the HFE is reading at 157. That's the current gain of the transistor. So let's see what happens if I plug it in. So the NPN holes. Well, it's reading 175. That's not the same as 157, but it's in the ballpark. And considering the crudity of the measurement scheme here, you know, it's not bad. It gets you in the ballpark, and I think that's pretty much all they promise with the model. Now let's hook up the PNP transistor. Shows that it's a PNP silicon. It was red, green, blue. Let's see. I have it connected blue, green, red. So emitter, base, collector. So it has the same pinout as the NPN. And it's showing an HFE of 143. And we plug it in, and we get 153 compared to 143. So, again, in the ballpark, a useful, if not precise, reading. So that completes the demonstration of the unit. There's this padded case, which is not marked Heathkit. I don't know if it's an original case that Heathkit provided for this meter. It's not too dissimilar to cases I have seen them provide with other handheld things, but it's not exactly the same. This may just be a generic zipper case that fits meters of this general size. But it does fit it very closely, which suggests to me that it's the original case. Now this meter was very clearly well cared for. It has signs of use, but it's not been beat up. It's probably been kept in its case most of its life. And you know, probably got good use out of it. It's obviously been kept in calibration, and that doesn't suggest a meter that was thrown in a box decades ago and never touched. And the test leads fit in the little pocket here. These are, with all the accessories, these leads are a little bulkier than the original leads, but I think it'll still fit. Yeah, a little tight, but it's fine. The padded pouch will protect the front of the meter from anything there. So let's take a look at the manual for the IM-2320. This is a look that's different from the majority of Heathkit manuals, at least as far as the cover goes. This is definitely later Heathkit manual design. And having looked at and used a great number of Heathkit manuals, I found that the quality on this one, not so much the assembly instructions and descriptions, but just proofreading. There's a lot more mistakes in here. This is probably the original version. I don't know if they made any revisions. This one is copyrighted 1986. So it starts out as usual with an introduction, specifications, the different ranges and their relative accuracies, and the so-called burden they put on the circuits they're measuring. It's sort of an old-fashioned term, but it's pretty clear what they mean. Talks about, you know, maximum overload protections and things like that. And they continue over here with the things like capacitance, diode checks, and continuities, transistor measurements, required tools, introduction to resistors and capacitor markings. There are two circuit boards, And the instructions start out with the front circuit board, which is the smaller one. Step-by-step assembly. And in this regard, it seems like it's very much in line with earlier manuals. They didn't seem to cheap out on this. And there is not really that much to do on the front board. The rear circuit board, which is the bigger one. Parts list, and then all the assembly instructions. Oh, that's interesting. It's like there's a, I don't even know what that is. Little piece of plastic from something. Got stuck in there. Anyway, don't want to bore you with all that. Then we get into the operational tests. Then the calibration. You can use it, do it using internal references, a couple of parts that were provided with the kit that are pre-measured, and their values are written into the manual. You can use laboratory standards, so there's alternate calibrations. And then final assembly. Then there's the operational section telling you how to use the thing. Operating characteristics for all the different aspects of it. Interpreting the display, connecting the meter to circuits. How to do all the different types of measurements. It's pretty comprehensive, very thorough. Lots here to read, pages and pages of it. Then there's the troubleshooting section. And the usual charts of likely things that would go wrong for various types of symptoms. A fair number of pages of that. Then we get into the general circuit description. Then the detailed circuit descriptions, starting with how the basic analog to digital converter works. Then how the function range and control switching works. And I found a fair number of errors in here when I was perusing it. Then we get into more detail on the conversion circuits, such as the AC to DC converter, the oscillator drive and filter circuits for capacitance measurements, the power circuits, the tone generator for continuity, and then it talks a little bit more about calibration components that are provided with the kit. Page of semiconductor identifications, and then a page that talks about the pinouts for the different ICs. And really there's only 3 types of ICs here. There's there's the main 7106 monolithic digital voltmeter IC. Does most of the work. There's a quad NOR gate, a quad NAND gate, both CMOS, and then there's a dual op-amp package that are used in a few places, and then of course the LCD itself. And that's the end of the manual, other than the customer service page. Now that's the main manual. I should have clarified. In addition, there is the illustration booklet. I always thought these things were a combination of a benefit and a curse. It's nice that they had a separate book that you could have laid out apart from the main manual, so you didn't have to have as many fold-out pages and things. At the same time, I found that many times these were kind of unwieldy. I don't even have room to lay this out on my desk here. But it has a lot more detailed diagrams and parts identifications. When I go into the part of the video that talks about the selector switch, here's a picture of it as far as the detents. I didn't describe it very well when I shot that part earlier. Various chassis wiring, shield installation, some of the different calibration steps supporting diagrams, final case assembly, a diagram of the front panel and everything that's on it. And then we get into the block diagrams. These are used to support the text in the circuit descriptions. So we have the basic internal parts of the 7106 monolithic voltmeter IC. It doesn't describe how it does the integration, but it talks about its power supply functionality, its reference voltages, and its backplane drive and things like that. Then it does talk here about the integrator function of the IC, how that works in block diagram format. It talks about the dual slope measurement strategy that I won't go into here in any great detail. And another pictorial to support that same thing. Timing diagrams. This is mostly pertinent to how the LCD works. And some more supporting diagrams for that. And then this is a block diagram of how DC voltages are handled by the circuitry. How capacitances are measured. Diodes. Transistor HFE measurement. I have noticed the disparity in the quality of the documents here. Some of them were done very traditional Heathkit hand drafting. Some were clearly done on some fairly early personal computer schematic drawing software. Other ones are pretty chunky and done by a person with different standards of drafting or different software or something. Then you have your circuit board diagrams, the so-called X-ray views for the switching. These were useful to me in trying to figure out some of the errors in the schematics, things that just didn't make sense. And I was able to trace the foils much more readily on this diagram than I could on the assembled circuit board, and found out the errors in the schematic diagram from that. And then that's the end of that. So here's the ginormous schematic, and not really any reason I can think of for it to be that big. It would have been a lot more convenient to just print the diagram smaller. It still would have been plenty big and have it take up half as much paper. It also has some, in some places, some questionable drafting practices for schematic diagrams, you know, just sort of obtuse things about it. Makes it hard to understand what's going on. And it has sort of weird things like, you know, all these switches, it just gives you the switch identifier, but it doesn't tell you what they mean. And there is a chart over here that kind of sort of helps you with that, but I found going through it that it's not complete or completely accurate. It has errors in it, it has things that don't make sense. And then reading the circuit description, it would say something contrary to this and this. So I just figured out what they must be and penciled in their functionality and made little notes and things. It also just has flat out mistakes in it. You know, a very important one is, you know, misidentification of a power supply for this IC, and there's, I don't know, several other ones scattered around here. So again, I'm not impressed by this diagram. Heathkit has definitely done better ergonomically and functionally, and I'm not going to use this. I've redrawn it all in ways that are going to be a little more manageable. So here's my little sketch of the power supply circuit, both external and integral to the Intersil 7106. That's again the monolithic digital voltmeter IC. That's the heart of this meter. Once you got to a certain point in the early 80s and the 7106 came out, and its companion, the 7107, the 7106 was for LCD displays and the 7107 was for LED displays. Otherwise they were functionally the same, and the front end, the analog part, was identical. So I'll start out with the power supply, which is pretty simple. 9-volt battery and a power switch. Can't get much simpler than that. There's actually a couple capacitors in here that I didn't show for clarity. The battery's plus side produces the VDD signal, and the negative side produces the VSS signal, and then there's circuit COM or circuit ground, which is not either side of the battery, nor is it in the middle. It's actually 2.8 volts between VDD and circuit common or circuit ground, and as much as negative 6.2 volts between VSS and common. Now you may notice that those add up to 9 volts, which is the voltage of the battery. If the battery's voltage depletes over time and use, the 2.8 volt part remains constant. It's regulated, and the negative 6.2 will decrease. It'll become negative 6, negative 5.8, whatever. It'll decrease in voltage between these 2 points. Now how does that happen? Where's the regulator? That's where we get into the internal power supply functionality of the 7106. So this is a bit of a simplification, but it'll get the idea across. VDD, or 9 volts, is connected to the VDD pin, pin 1, and internally there's a power supply circuit that, for our purposes, we're calling constant current sources and Zener diodes, just to keep it simple. And both of those connect out the VSS pin, pin 26, to the VSS power supply rail, which is the negative side of the battery. So looking at the first one, we have a 2.8 volt Zener diode equivalent and a constant current source returning to VSS that produces a voltage of 2.8 volts between VDD and COM, which is tied to circuit ground or circuit common. So as long as you have a battery connected and it has any voltage on it at all, and as long as the 7106 is working internally, there will be 2.8 volts between VDD and COM. That's this over here. Then there's a similar circuit also from VDD through a Zener diode equivalent, through a constant current source returning out VSS. But in this case it's a 5 volt Zener equivalent. And through a resistor, that point is connected to the V-test signal, pin 37. So that point will be 5 volts below VDD. And we'll talk about that later on. That's really only going to come into discussion when we're talking about the fine points of how the DC, the LCD works. Just a little bit more about the 7106. It's a dual slope integration auto zeroing scheme that's used here. And without going into it too far, the earlier digital voltmeters and digital multimeters used a single slope where they would just charge up at a linear rate a voltage from, you know, 0 or some other lower voltage up to a higher voltage, and when it starts charging, it starts a counter which is run off of a precision digital clock, and whenever the slope, the rising voltage, crosses the input voltage, then the clock stops, and whatever is in the clock is shown on the display. And if it takes longer to reach the input voltage, then there will be a larger count and therefore a larger number in the display, and vice versa. So that's a single slope, but it has problems. It works, but it's not as stable. It doesn't compensate automatically for variations in values of the components in the integrator circuit, so it's not as good. The dual slope method, you ramp up and then you ramp back down and then ramp up and ramp down again, and different tests are done on the up slope and the down slope, and by doing so the circuit that surrounds that is able to compensate for drift. It can compensate for power supply voltage differences and temperature and all sorts of things, and it just makes for a more stable, accurate multimeter. So there are a few support components. There's a capacitor, a resistor, and another capacitor tied to the integrator, buffer, and auto zero part of the internal circuit. Auto zero is also a function. If you look at some of those older meters I showed from Heathkit that preceded the use of things like the 7106 or 7107, there would be zero trim pots on them, and occasionally you'd have to re-zero them. Once it went to chips like this, they auto-zeroed themselves, so there's no longer calibration functionality in the meter where you have to be tweaking potentiometers and things. It simplifies things a lot, makes it a lot more reliable and bulletproof. But anyway, these are external components which are not part of the chip. Then there's a reference capacitor, C-ref, which is external to the chip, connected on 2 pins. There's an internal oscillator that the chip uses for its own internal digital functionality, and that consists of a RC network. There's the R, there's the C, connected to the OS1, OS2, and OS3 pins. The oscillator runs at about 40 kilohertz, and after being divided down and processed through the dual slope division and the other conversions that are going on inside the 7106, it results in about 2.5 conversions or 2.5 display updates every second. So not a speed demon, but reasonably fast. And I was saying before that once the 7106 and 7107 came on the market, whenever it was, the early 80s, I believe, then, you know, everybody just used it. You find tons and tons of stuff that just, they scrapped all the brute force, complex, discrete components approaches they had, and everybody just used these. You know, there wasn't even any point. These were so good, and they're still made and used today. Originally it was Intersil, and then I think it got sold to Harris, and I think somebody else does it now, but you can still buy these. They're still used. And in the early 80s, at my engineering job, I used a lot of 7106 and 7107s. Anyway, so going back into the theory of operation of this IC, it has 2 analog inputs, and they're like op amps, basically. They're differential. It doesn't care what the voltage is from either of these wires to ground or circuit common. All it cares is what is the voltage between those 2 pins. And the IC is designed to work in a range of minus 200 millivolts or minus 0.2 volts up to positive 200 millivolts or plus 0.2 volts. And there's a external capacitor across those just for stability. Now on this particular meter, the input low signal is always tied to the COM pin and to circuit common or ground. That's not always the case, but on this particular meter that's the way it's done. So the input low is always electrically the same as circuit common. And we know that that means it's always held at 2.8 volts below VDD. Now there's another input that's very much the same, and this is the reference input. The pins are reference low and reference high. They also have a stability capacitor, and a reference voltage is applied here. The way the IC uses those is it measures the voltage from here to here, and it measures the other voltage from here to here, and it takes the ratio of those two voltages, and it's the ratio that is displayed on the meter's display. So it's not enough to just say, well, what's the voltage here? It also is important to know what the voltage is here and what the ratio is between those. The way this meter is designed, it normally keeps this reference input static and basically tries to pretend like it's not there, so it can just use the main input. But in at least one mode, it's very critical to the operation of the meter that both of those are used, and I'll talk about that in more detail. So returning to the Heathkit schematic just for convenience, here is a picture of the LCD, schematically pictured that is. Now unlike an LED display, which is usually going to be multiplexed, so only one digit at a time is turned on, in this circuit and using the 7106, the display is not multiplexed, or if it is, it's internally multiplexed in a way that's not pertinent to the external wiring. It does not treat the display from a wiring standpoint as if it was multiplexed, and it can't be because there are no digit commons. Every segment and the decimal points and the minus sign and the low battery indicator all have their own individual electrical connections back to the 7106. The basic way an LCD works is that you've got all of these segments that are expected to become visible, and they are just done with conductive coating that's thin enough to be transparent, put on one piece of glass, and then another piece of glass that's the whole background of the display has another transparent layer of conductive coating, and that's the back plane. And a voltage is applied between any given segment and the back plane, and if the polarities are opposite, in other words, if there's a positive voltage on a segment and the back plane is negative, then that segment will not light up because LCDs don't generate light, but it will become visible using the ambient light in the room. If, however, the polarities of the signals on a segment and the backplane are the same, if they're both positive at the same time or both negative at the same time, then that segment will be transparent and it's as if it isn't there from a visual standpoint. So that's the key to this, and it'll come into account later, where the backplane is constantly changing polarity. It's positive, then it's negative, positive, negative, going back and forth very quickly. And the individual segments are positive and negative going back and forth. And it's the phase relationship that determines whether they're going to be visible or not. If they're in phase with the backplane, they're invisible. If they're out of phase with the backplane, then they're visible. So here's my little sketch of the way the parts of the display that are not driven by the 7106, how they're handled. And this is handled more discreetly by the meter circuit, not by the 7106 circuit. And that's because all the 7106 cares about is those low voltages, for example, plus or minus 200 millivolts, which obviously needs to be scaled from the real world voltages or currents or whatever. So the meter cannot know where you want the decimal points to be. All it can do is show the raw numerical value. So separate circuitry in the meter determines which decimal point should be on, given which range you're in and how that's being scaled. There's only 3 decimal points that are actually useful to us here. Decimal point 2, 3, and 4. Decimal point 1 would be at the right of the least significant digit, and there's no reason to have a decimal point there in this meter. It could be in some other application, but not in this particular meter. So we don't have to worry about driving decimal point 1. So let's look at how this works. We have some switches here, and these are actually much more complicated than drawn, but it's a group of switches on the main rotary switch which are hooked up in parallel. For one group is to control DP4, another group ends up controlling DP3, another group controls DP2, and those are connected to VDD, which is plus 2.8 volts, as we already talked about, and those are applied to the inputs of 3 XOR gates, and that's a CMOS IC, and it runs at 5 volts, but there is no 5 volts in this meter. The positive power supply for this IC is VDD, which is 2.8 volts, positive 2.8 volts. The other side of the power supply for the IC, it's V minus if you will, is that V test signal, which I already showed is 5 volts below VDD. If you do the math, that ends up coming out to minus 2.2 volts. That's all relative to the circuit common or circuit ground. So you have essentially a minus 2.2 and a positive 2.8. You add up, or you figure out the difference between those, and that's 5 volts. So this IC is being powered from 5 volts, but it's not 5 volts measured from circuit common. But as far as it knows, it doesn't care. It just knows it has 5 volts between its power supply pins. And that's when its outputs go logically high, they won't go to 5 volts, they'll go to 2.8 volts. When they go logically low, they'll go to minus 2.2 volts. So let's look at what happens here. These 3 inputs are pulled low most of the time, which is V-test, which is minus 2.2 volts. And the switches can pull them high, which is 2.8 volts. If those switches are closed. So let's say that we're in a range where you want decimal point 4 to turn on. So that switch closes and it pulls the input of this XOR gate high to logic 1 against the pull down resistors that are trying to pull it to minus 2.2. And when that's true, then we can think of this point as being a logical 1. Now, meanwhile, the other input of that gate is tied to the backplane output of the 7106. So we know that's constantly and rapidly switching between minus 2.2 volts and positive 2.8 volts. And the way an XOR gate works is its output is only logically true or on if one and only one of the inputs is logically true. If both are logically true or neither are logically true, then the output will be logically false. So let's take a scenario where at the very moment the backplane is minus or low. Now we have this pulled high logically. Well, my computer always goes ping just when I'm trying to talk. So this is pulled high, so we have a high and a low, and that would normally mean the output is a high, so it goes high. And what is the backplane at the moment? It's low, so we know that will illuminate that decimal point. Now when the backplane flips to be logic high, now you've got a high and a high, which gives you a logic low on the output. So now the decimal point's driven low, because a high and a high on an XOR gives you a low on the output. So now you've got a low on the decimal point, but the backplane is high now. So once again, they're out of phase, and the decimal point still lights up or becomes visible. But if you open this switch, you don't want the decimal point to be on anymore. That input gets pulled to logic low, minus 2.2 volts, and now it works oppositely. So the output will always follow the backplane, therefore it'll always be in phase with the backplane, therefore that decimal point will always be invisible. And the same exact thing happens for the other two decimal points. There is a special version of the ganged switch which is called DP1 on the schematic, but in reality it's not to control a decimal point. Well, it does peripherally, but not directly. It's really there whenever you're in the diode test or continuity test modes. That's when this switch is closed. So when that's closed through this diode, it causes decimal point 4 to turn on, just as if this switch were closed. And that's because when you're in those modes, you have a fixed decimal point at the most significant digit. It also goes out and powers the continuity buzzer circuit, which I'll talk about separately. It acts as the power supply for that. And then there's a pull down resistor to VSS, or minus 6.2 volts. And finally there's a fourth XOR gate in this IC, and this one is used for the low battery indicator. So the logic here works just the same as it did up here, but in this case we have a voltage source driven from VDD, that's plus 2.8 volts, through this resistor, and then a 5.6 volt Zener to VSS, or minus 6.2. And I made a little sketch of what that means. So here's VDD up here, here's VTest down here. Remember that that's how the IC is powered, from VTest to VDD. So as far as the IC is concerned, and remember it's a CMOS IC, it's looking at a 5 volt span from VDD to VTest. And with CMOS, the switching threshold, in other words the voltage at which the inputs think it's either logically high or logically low, that's going to be halfway between those, 50% of the voltage, which here works out to be 0.3 volts, positive 0.3 volts. So any signal applied to the input that's greater than that will be treated as a logic 1. Any signal lower than that is treated as a logic 0. So we have this input now, and it's looking at this circuit from VDD to VSS with the 5.6 volt Zener, and we find out that that nominally gives us a negative 0.6 volts on the input. Well, that's lower than the 0.3 volts. There's actually 0.9 volts between them. The 0.3 is right here, and there's the negative 0.6. So it's definitely lower than the threshold. The IC sees it as a logic 0, and therefore it does not turn on the low battery indicator. However, as the battery voltage sags, and remember this whole thing is across the battery, the Zener keeps its part constant at 5.6 volts, and that means that it's progressively dragging this pin in a direction that ultimately puts it on the other side of the threshold, so that it looks like a logic 1, and through the same circuit magic that happened up here, it now starts energizing the low battery segment out of phase with the backplane. So then the low battery indicator turns on. It's a little counterintuitive how this works, That's why I made this picture here, because it helped me to understand it. Anyway, I think that's enough to say about how the LCD works. So here's a simplified view of the voltage measuring front-end circuitry of the meter. This is all external to the 7106. I didn't cheat here. I didn't really leave anything out. I just left off everything that's not pertinent to voltage measurements. So you have the volt-ohm jack for the test lead. That's the positive input. And then you've got the common jack, which is tied to circuit ground or common. And you apply a voltage between those two. If the meter is currently in one of the DC volts modes or one of the AC volts modes, then this jack is connected to the top of this big voltage divider made out of 6 precision resistors. A 9 meg, a 900K, 90K, 9K, 900 ohms, and 100 ohms. If you add all those up, it becomes 10 megs for this entire assembly. And then the bottom of it, once again, if you're in any of the DC volts or AC volts modes, the bottom of that divider is connected back to common. So you impress whatever voltage you're measuring across this big divider. Then, depending on which range you're in, 200 millivolts, 2 volts, 20 volts, 200 volts, or 1000 volts, or 750 if it's AC, one of these switches will close. Now, there's another switch down here which is not actually used for voltage measurements. This group of resistors gets reused in another mode, and in that case this switch is important. But for normal voltage measurements, only these 5 positions are important. So that ends up dividing it down. So let's say you're applying a signal that's less than 200 millivolts. You would close this switch up here. That would put you in the 200 millivolt range, and then this whole divider is sort of ignored. It just acts as a high impedance load across whatever you're measuring, but you actually don't divide anything down. The voltage just comes straight out through the 200 millivolt range switch, and then depending on whether you're in DC or AC volts, you can either go straight through or you have to detour through the AC to DC converter. And then there's a voltage, couple resistors in series, a 1 meg and a 100K, which is 1.1 meg, which are there for other reasons besides voltage measurement, but they're still there. And they're basically transparent because compared to the very high input impedance of the 7106's inputs, these resistors are as if they're not really even there. It doesn't even notice them. They're comparatively such low impedances. And then that's applied to the input high. The input low is just tied right to circuit common. In other words, right back to the common input. And since we already know the signal we're measuring is less than 200 millivolts, it falls within the plus or minus 0 to 200 millivolt range that the 7106 is expecting. Now, what if you gave it a 2 volt signal? Well, that's more than the IC is expecting, so we have to divide it down. So in this case, we tap off the 9 meg resistor, and then there's 1 meg below it. So we're dividing by 10. We're taking 1/10 of the voltage. We're just dividing down by 10 and then coming through this switch, and then the same thing happens progressively. And if you're up in the like 1000 volt range, now you take a progressively smaller slice of the pie because most of the voltage is being dropped up here, and now you're taking orders of magnitude lower, and it happens to now fall within the range that the IC is expecting. What about the reference input? Those are important. Well, there's a resistor voltage divider between the VDD, or plus 2.8 volt signal. It's an 18.2K, then a 200 ohm trim pot, which is the DC calibration, and then a 576 ohm and back to circuit common. This is set up so that when the pot is in mid-range, you get 0.1 volts, and that's applied to the reference high. Again, there's these 100Ks in series, but they're not even there as far as the 7106 is concerned, because its own impedance is so much higher. And then the reference low just makes it way back, essentially to common. So we're comparing 0.1 volts here with anywhere between 0 and 200 millivolts here, and that ratio ends up being what's displayed. So that's the essence of the voltage measurement front-end circuit. So here's amps. Now, in the case of amps, we're not measuring across something, we're measuring in series with something. And with the amps, we don't just have a pair of jacks for our test leads, we have 3 that we can use. One of them is always on common, and then if we're in the lower ranges, the milliamp ranges, the positive test leads on the milliamp jack, but we can use the 10 amp jack, which would be here. Let's just look at the milliamps. So the milliamps has circuit protection. There's a fuse, that's a 1/4 amp fuse, and then there are back-to-back or inverse polarity parallel diodes going back to common. In normal use, the voltage developed between here and here should be less than the voltage that would forward bias these diodes. So it's as if they're not even there. But if you did get a situation where you had too much current going through the circuit, then it would develop a higher voltage, which would then forward bias one or the other, or maybe both if it's AC, one of these diodes, and then there's a path through those back to here so that extra current goes through there, and the idea is hopefully it'll blow the fuse. If that happens, it's making like a short circuit, and the fuse should blow, thereby protecting the meter. So let's look at situations where we don't have an overload. We come in here with our milliamp signal. It goes through a big shunt resistor made out of a 990 ohm, a 9 ohm. There's a couple orders of magnitude difference there. And then a 0.99 ohm, so it's almost 1 ohms. And then a 0.01 ohm, and then back to circuit common. If you add all those up, that becomes 1K, 1 kilo ohm, 1000 ohms across the entire shunt. And then depending on whether you're in the 200 microamp range, the 200 or the 20 milliamp range, or the 200 milliamp range, you bypass parts of the shunt. So let's just look at 200 microamps. Let's say we're in that range and we're running something less than that in the milliamp input and out. So that let's just say it's 100 microamps. That goes through all of these resistors before coming back out. So the voltage developed across that will be half of the voltage in this range. So the IC is good with it. Now if you have a higher current, say you're up around 10 milliamps or up to 20 milliamps, now you come in here and you join the shunt at a lower point, so it's dropping voltage across a smaller resistor, but because the current is bigger, you end up developing the same kind of voltage across the shunt, and therefore it's still in the same range that the 7106 is good with. And likewise for 200 milliamps, a smaller shunt but a larger current ends up with the same voltage coming out. Now if you get above that, you make a big jump from the 200 milliamp range up to the 10 amp range. In this case we're just going across this minuscule 0.01 ohm, a pretty tiny shunt, but again the current is very high, so it once again develops the same range of voltages that the IC is looking for. Well, then how does the signal get back? Well, let's say we're using the 10 amp range, so the current is actually going this way. You're developing some voltage in the range of up to 200 millivolts. It's actually going to be 100 millivolts with 10 amps through this. Well, that just goes backwards through these diodes, or these resistors rather. Keep in mind that these are going to be less than 1K, so it's an insignificantly small amount of resistance. As far as the rest of the circuit's concerned, that's just a piece of wire. So that voltage then is applied up here. It either goes directly around the AC to DC converter, or if you're in one of the AC amps ranges, it goes through the AC to DC converter. And once again, there's these two series resistors, just like in the voltage mode. They're insignificant compared to the impedance of the 7106, so they just appear to be a piece of wire. The input low is tied back to circuit common, and the voltage reference is just the same as it was with voltages. You're using the DC cal voltage off the trim pot for ref high. Ref low is tied back through either the DC amps or the AC amp switches and back to circuit common. So once again, it is very much like the voltage range in that regard. But that's the way amps are measured. So here's the AC to DC converter. We've already talked about the volts and amps ranges, which are the only ones that normally use the AC to DC converter. That's not completely true. The capacitance test also uses it, but the majority of functions that use it have already been discussed, so I'm going to dive into it here. So here's the input circuit from all the switches and resistors that come up front, and it could be bypassed with a switch, but if we're using it, the AC signal comes in here and a proportional DC signal comes out here. Now the goal is to rectify the AC signal to turn it into a DC signal and do it in such a way that it's an appropriate proportional signal. So you can't just put a rectifier in there, because the rectifier has minimum voltages at which the diodes will conduct. So it would ignore lower voltages and give you a disproportionate result for higher values. So we use what's called a op-amp precision rectifier circuit, and this is Heathkit's favorite version of it. It's not exactly like the textbooks, but it's easy enough to figure out. So because it's possible that you might have a situation where this has to work in DC, even though in normal use it would never see DC, we still have a classic negative feedback through this 9.1 meg resistor. You apply your input to the plus input of the op amp, and you have negative feedback. That makes this into a voltage follower as far as DC is concerned, so the output would be the same as the input. Now, if we put an AC signal into here, that passes through, and it's presented to a DC blocking capacitor. So no DC can get through here, only AC can get through. And now you're presented with a feedback path that has to go through one of these two subpaths. If the AC signal currently has a positive here, then you're going to positively bias or forward bias this diode, and the feedback path will be this way. If it's negative, then the feedback path will be this way through this diode. And they have the same values, so the op-amp doesn't care. The thing to remember here is that the op-amp is assuming it has feedback, it's always going to try to make its output be whatever is necessary to result in the plus and minus inputs being the same voltage. So if it puts a signal out here which if it just went through the diodes, it would be attenuated by the forward voltage drop of the diode, but that dropped voltage is applied back through the feedback and it says, hey, I had 2 volts here, or let's say half a volt, and now I've got half a volt minus the forward drop. So let's just say, for example, I've got 1 volt here. It's at a given moment on the AC waveform. The outputs say the same voltage. I'm not going to worry about any differences in gain for the moment. And that gets 0.7 volts knocked off of it. That's the forward voltage of a typical silicon diode. So there's only 0.3 volts, and that gets wrapped around in the feedback path and applied to the negative input. Well, it says, well, I have 1 volt there and I've got 0.3 volts here. I need those to be the same, so it boosts its output, making this a higher voltage, and it keeps boosting it until whatever comes out of this diode after its drop is subtracted now matches the input signal. And therefore, the voltage out here is the same as the input voltage, and ignoring the voltage drop of the diode. It's as if it didn't even exist, thanks to this feedback and the operational amplifier here. Now, if your polarity is opposite, it does the same thing in the other direction. And again, the feedback is only through a DC blocking, so it doesn't work if there's any DC component to the signal. It only works on AC. Well, this isn't the end of it here. These resistors don't just go back here. What they actually do is, whichever one of these paths is conducting actually has a voltage divider here. So let's say this is the path that's conducting. It goes through this diode, goes through this resistor, and then through these 2 resistors to ground. So this is your voltage divider. So it's taking whatever comes out of the diode, dividing it by the ratio of the voltage divider components, and it's the result of that division that gets fed back. Well, one of these resistors is the AC calibration trim potentiometer, and during the calibration of the meter, this is adjusted until it results in exactly the voltage we want, with the DC output matching the average of the AC input voltage, except DC instead of AC. So this is your calibration. And finally, how do we tap off of this? How do we get the signal out? Well, we get it out here. We get it right off the diode. And since we're looking to convert AC signals into DC, it might as well be positive DC. We could have tapped off of here and had it all be negative, but the there's no reason to give a negative sign to a converted AC signal. We might as well just show it as a positive DC value. So we tap off the positive one, so we get a positive DC voltage. And there's a little RC filter here, and then that's the output of the AC to DC converter. It goes through a couple other resistors and some switches on the way to the 7106. And you may ask, well, we're only looking at half the waveform here. That's true. We don't measure the result when the waveform is in its negative half, but the op-amp doesn't care. It's processing the entire AC waveform through either this path or this path, but we're only looking at half of it. But the voltages are the same. We're just not looking at the negative part of it. But you end up with a signal that's, half a wave and then nothing, then half a wave, then nothing, and so on. That's what this filter is here for. That fills in the gaps. It averages it out so that you don't have a bumpy DC signal coming out of here. So that's how the AC to DC works. Okay, ohms, the resistance mode. This gets a little more interesting because unlike voltage and current, we're not relying on an external source of energy, either voltage or current, to power the meter circuitry. It all has to be self-powered. So it's a little more complicated. There are several different ways to skin the cat. There are methods that use a constant current source, and then that's fed through the resistor under test, and the voltage across the resistor is measured by a voltmeter circuit and displayed. So that's one way of doing it, and indeed that's the way about maybe half of Heathkit's digital meters work in their ohms mode. This one works a little differently, and it can work this way because of the 7106's ratiometric two inputs, which are also differential inputs, the reference input and the normal input circuit. Because of that, we don't need to have the constant current supply that some other meters have for their ohms. So let's look at the way it works here. What we have here is a precision voltage supply, which is programmable, and it's programmable depending on which range we're in of the ohms function. We start out with VDD, that's positive 2.8 volts, goes through a resistor, then it goes through some diodes in series, and then to circuit common. Each of these presents a 0.7 approximately forward voltage drop. So, if you had two of them in series, that's about 1.4 volts, and so on. There are two switches here, and there's a little table. If you're in the 200 ohm range, neither of these switches are closed. They're both open. If you're in the 2K range or the 20K range, this switch is closed, the other one is open. And if you're in the 200K or the 2 meg range, then this one's closed. All that it amounts to is what voltage is presented to the base of this transistor. If both of these switches are open, then these diodes are not even there as far as the circuit is concerned, and all you're doing is applying the 2.8 volts to both the collector and the base, and you essentially get the same voltage here minus the forward voltage drop of the transistor, and that voltage is dropped across this 100K resistor to ground. But if you're in one of the other ranges, for example, if we close this one, now you've got these two forward voltages, approximately 1.4 volts, to ground, so it's holding this at a lower voltage than it would be normally, and therefore the output of the transistor will be proportionally lower. And if you close this one, now you've got 3 voltage drops in series, which makes the base even lower, hence the emitter output across this resistor is lower. So there's basically 3 voltages that can be out here depending on which resistance range we're in. And that's connected to the outside circuit through 2 different parts of the selector switch when it's in the ohms range. One part of that is applied directly to the reference high, and the other part is applied through this big bunch of resistors, through a diode, through a positive temperature coefficient element. That's a resistor that its resistance goes up when its temperature goes up, and it goes down when the temperature goes down. And then a 1K 2 watt resistor, and then out the V ohms or volts ohms jack of the meter through the resistor under test, and then back to circuit common, or back out, but it's tied to circuit common. So what do we actually have here? We have a precision voltage reference that's applied to some resistance that's programmable according to which range we're in, and then that goes through the diode, a couple of resistors, and then the resistor under test and back. So you've essentially built a big voltage divider here with a precision regulated voltage at the top end and circuit common at the other end. The 7106's reference inputs are measuring across this variable resistor. They're doing it by virtue of these switches. If they're both closed, it's as if this point here is tied to here, essentially the top of the resistor divider, or wherever it would go according to which range switch is closed. So then that same current in a series circuit, the current always has to be the same everywhere in the circuit. So the current through here is the same, the current through here is the same, the current through the resistor under test is the same. So the same current that's causing a voltage drop across this variable resistor and being measured by the reference input, that same current is causing a voltage drop across the resistor under test, and that's being measured by the normal input circuit of the 7106. So it doesn't matter what the voltage is. If the voltage goes up a little higher or lower, you know, if this circuit isn't as precise, if the battery voltage changes, you know, whatever. Now keep in mind that that 2.8 volts is regulated by the 7106. That's where it's coming from. But even if none of that worked and you just had this tied to a battery and the battery voltage could sag over time, this doesn't care because the voltage drop across this is always proportional to the voltage drop here, and the 7106 is ratiometrically measuring the voltage drop across this one and across this one via its two separate inputs and displaying the ratiometric result. So it doesn't matter what happens out here, it always stays accurate. It's superior to the other scheme of using a precision current source, constant current source, and then measuring the voltage across it, because that system cannot track drift. If your precision constant current source isn't that constant, if it has any small differences in it, then that will be reflected in decreased accuracy of your ohms measuring function. But with this scheme, this very simple scheme, it's impervious to pretty much any change in the circuit, except for very small changes in these resistors, of course. These are precision resistors, and they shouldn't change much with over time or with temperature. But if they did, that would throw your measurement out a little bit because they're no longer wherever you calibrated this thing to. And guess what? There's no calibration on this thing. There is no calibration for the ohms mode. It's just all based on how accurate these resistors are, and these are like 0.1% resistors, so that's where all the error in the circuit comes from those. Well, this diode here is just there to protect the circuit in case you connected, instead of connected the test leads to a resistor, you connected it some voltage source. Now that voltage source is being put directly across the input pins, but you know, up to a certain level, the high impedance here can protect itself against that. The diode is here to deal with some eventualities of connecting things funny. If you ended up getting a high current going through this path, again, if you connected things wrong with the test leads, then you'd end up with a lot of current going through here, and that causes this positive temperature coefficient resistor to increase its value, its resistance dramatically, which then cuts down on the current and protects itself. And also, if you develop too high a voltage at this point relative to circuit common, then this reverse connected NPN transistor starts conducting. It conducts in reverse, but a standard bipolar transistor connected in reverse like this, with its base connected as this one is, it behaves like a Zener diode. So this is basically just a poor man's Zener diode. So again, it clamps the voltage here to no more than a certain amount. So that's another safety to prevent the meter from being damaged if you do something dumb with your test lead connections. Okay, diode test and continuity. The circuit works the same way for either one, and it's sort of related to the ohms testing mode, but not exactly the same. So we don't use the 7106 in its ratiometric functionality. It's used more like it is in its voltage measuring mode, where the reference inputs are just tied to a voltage, a DC calibrated voltage derived from the VDD and these resistors, and then applied to the reference input, and the reference low goes through a switch back to circuit common. So the reference voltage is sitting here at 0.1 volts all the time. So all we're really changing now is the input voltage. So let's see how that's derived. So we have either a diode out here that we're testing to see if it's good or not, or we're using it as a continuity checker where we just have the test leads measuring across a wire or a switch or something to see if it's closed or open, if there's continuity. So either a diode or a wire making connection or not between the volt ohm input and the COM. And this looks pretty familiar here. This is part of that same circuit that was used in the ohms mode. So here, instead of coming through a big resistor network above this, we tap into it through a switch that's closed in the diode test mode. It comes from VDD, that's the plus 2.8 volts, goes through a 1.5K resistor that wasn't there in the resistance mode. It has that same reverse connected transistor that acts like a protection zener to ground. It still has the positive temperature coefficient element and the 1K resistor in series with that. So that provides your positive voltage source essentially, which then, again, if the meter is in the diode test or continuity mode, this switch is closed and you've got this path to ground, assuming there's something connected there. There is adequate voltage applied here to forward bias normal silicon diode. So if you've got a diode connected forward, it should act like a short circuit almost, at least as far as the rest of this is concerned. So when my memory card just filled up there, I lost my train of thought. I'm going to try to regroup here. So we have the VDD plus 2.8 volts, switch, resistor, PTC, another resistor, then the switch, and then it goes through all of these resistors, and these are part of the voltage divider from the voltage mode. It's just coming in at the top, and then at the bottom, if you're in diode test or continuity mode, that bottom of the resistor divider is connected to circuit common. And across that whole thing is the diode you're testing or the thing you're trying to test continuity of. It's electrically across this. And if there is nothing out here, then you just have whatever voltage is dropped across these resistors, which is most of the voltage, because there's only 1.5K and whatever this is, and 1K, pretty small resistance up here, and then you've got basically 10 megs here, so pretty much the whole voltage is developed here. And then it comes down here, and it's applied to the in high of the 7106 through these resistors that up to this point didn't have any effect because the bottom wasn't connected in a way that made any difference. But here it's a 10-to-1 voltage divider, so we're taking a fraction of the voltage, you know, maybe 0.28 volts or something. And of course it's less than that because you're not tapping off the voltage divider at the top. In reality, you're tapping off at the 1 meg under 9 meg point, so it's already about a tenth. So it's already like, you know, 0.28 volts here, and then after you divide it down, you know, even more, than you get a voltage that ends up being in an appropriate place down here. I think it's usually closer to 0.1 volt that it sees most of the time. I didn't do the math, but I think it's in that ballpark. Anyway, so you normally have that on there, But then if you have continuity out here, it shorts this out, and now you've got essentially nothing. So it goes between two different values. And of course the input low is just connected to circuit COM like it always is in all the modes. So that's basically how the circuit works for just detecting if you have continuity or not, or if you have a diode connected that's functioning properly and it's connected forward biased. Therefore you can tell which end of the diode's the cathode. If you connect it backwards and you get the other reading, you know which way is which. But that's not all there is to it. In continuity mode, you don't want to be looking at the display, you want to hear something. So how does that work? Well, here we have an op-amp wired up as a comparator, and it's monitoring the same input as the 7106, and then its other input comes back here. This is that same precision voltage reference we had in, for example, the ohms mode, where we just have VDD, that's plus 2.8 volts, connected to this transistor with a load resistor on the emitter, and the diodes are out of the picture, so it's just conducting through here. Then we have a voltage divider that nominally produces about 20 millivolts at this point. So 20 millivolts is applied, and that is normally overwhelmed by the voltage that's developed here, so that the output is driving low most of the time. And but if you then connect continuity over here, which shorts all this out and lowers the negative voltage, now the 20 millivolts on the plus input overwhelms it and it drives the output high. So continuity, the output here goes high. No continuity, it goes low. Now that signal is connected out here, and this is the oscillator for the piezo buzzer, or the continuity beeper, however you want to look at it. This circuit only works when the meter is in the diode test or continuity modes, when this switch is closed. This IC here is a quad CMOS NAND gate. It's powered between VDD, which is plus 2.8 volts, and VSS, which is minus 6.2 volts. It's basically powered across the entire 9-volt battery, or whatever voltage it's putting out as it ages or gets worn down. Doesn't really matter. Normally, this input here is pulled low by this resistor, unless you're in diode test / continuity mode, in which case it's pulled high. Now this circuit here is a classic right out of the textbooks. 3-inverter oscillator with the 2 resistors and the capacitor. Normally this is shown as just simple inverters, 1, 2, 3. But here we expand them into NAND gates because 2 of them are being used as gates that can turn this circuit on and off. One of them is, as I already mentioned, if you put the meter in diode test or continuity mode, it pulls this input high, so now this gate can function as an inverter. Otherwise it does nothing and this circuit can't work. But if you've got it in that mode, now it can function and you get the feedback and you get the oscillation. The other thing is that in a similar fashion, this gate behaves the same way as this one, but its variable input is the output of this comparator. So, as I said before, when we have continuity or a forward biased diode under test, the output will be logically high, and that turns this gate on, allowing this whole thing to work. So, 2 different places we can enable or disable this oscillator, from the comparator or from this switch. Both need to be logically high for this to work. And this point here is oscillating at whatever frequency this thing is oscillating at, and it drives one side of a piezoelectric transducer. It's also driving the 4th inverter in this IC, which is inverting that signal and connecting it to the other side of the piezo. So when this side is positive, this side is, or when it's high, this side's low. when this side's low, this side's high, it's always driving it differentially. So whenever you're in diode tester continuity mode, and when this circuit up here detects that you've got a forward bias diode or continuity through a wire or something, and you get a logic high here, then this runs and the beeper goes beep, you know, that's how it works. So that's the whole thing for diode test and continuity. Okay, we're getting near the end of this lengthy description. So capacitance. This is one of the more interesting modes. It's got more parts to it, but conceptually it's quite simple. So here's a simplified version of it. This is using the concept that in an AC circuit, the capacitive reactance, which is part of the impedance of a capacitor, is proportional to the size of the capacitor, its capacitance, and its capacitive reactance slash impedance are proportional. So if we took an AC signal and say it's a sine wave running at 300 hertz, and you apply it to one side of a capacitor, and then you connect the other side to the negative input of a op-amp voltage follower, or in this case, since it's got this kind of feedback arrangement, it's got some gain, but it's an inverter, an inverting amplifier. And the output voltage is proportional to the capacitance, because as we know, on an inverting op-amp like this, the output is the signal times the ratio of the impedances of the input device and the feedback device. This is the calibration circuit. Actually, I'm sorry, I said that wrong. This is not the calibration. In this simplified version, it's just a variable resistance. In the real circuit, it's more elaborate, but let's just say it's a variable resistance. And the output here is going to be based on the gain of these two things working on the signal coming from here. And as this capacitance value changes, then its capacitive reactance and thus the impedance changes, and that changes the gain of this amplifier, and the signal coming out of here is more or less depending on what the value of the capacitor is. And then, but it's still an AC signal, and you want to make sure that you're only looking at the signal that is responding to this 300 hertz signal, not some other junk like AC hum or induced voltages or other garbage. You want to make sure you're only looking at the signal that's influenced by the capacitance. So in other words, it better be at 300 hertz. So there's an active filter that is set up as a notch filter or a bandpass filter. It's fairly narrow, so if the signal coming in is 300 hertz, it just passes it right through. If it's lower or higher than 300 hertz, it blocks it or greatly attenuates it. And if you've got a signal that has different components, like a 300 hertz component and a 60 hertz component, you know, some AC noise, for example, the 60 hertz part is attenuated way down, and the 300 hertz part passes through unmolested. So that's the general idea. It's using the fact that the impedance based on capacitive reactance is proportional to the capacitance. So when we actually flesh it out, we start out with a Wien bridge oscillator here. It's a classic Wien bridge oscillator. Op-amp with, it's powered from VDD on the plus side, that's positive 2.8 volts, and VSS on the negative side, that's minus 6.2 volts. And you might think, well, that's kind of squirrely, shouldn't it be the same voltage? Well, it doesn't matter, and the op-amp doesn't care as long as it's never expected to output a signal more than one of those voltages. It can't go more negative than minus 6.2 or more positive than positive 2.8. And the signal we're putting through it's smaller than that, so the op-amp is oblivious. It doesn't know it has these limitations or the disparity in positive and negative voltages. It doesn't care in this situation. But anyway, so you have a negative feedback in the configuration you would have if this was a non-inverting amplifier. And then you've got two filter elements, a series RC and a parallel RC, and the values are the same, 52.3K on the resistors, 0.01 microfarad on the capacitors. And what this forms is it's a high-pass filter and a low-pass filter, but it's trying to oscillate because it has the positive feedback, and it's trying to oscillate at all sorts of different frequencies, essentially, but because the feedback here through this and this path to ground, one of them is reacting in one direction for frequencies going up or down, the other one's reacting in the other direction, and the only place it's happy is when they both agree. So that establishes the only stable frequency, and that ends up in this case being 300 hertz, like I mentioned in my simplified diagram, and it's an approximate sine wave. Normally in a Wien bridge oscillator, this element over here is made variable in a way that stabilizes the amplitude, but in this situation the amplitude stability isn't as important, so they have not stabilized it here. It's just a normal resistor. And then it goes through a driver which provides another inversion, and you've got a 10K input, and with the capacitor calibration pot and this resistor here, this is just really a driver circuit, and here are the 3 pins for one side of the capacitor and 3 pins for the other side. This is the jack on the front of the meter where you can plug in capacitor, and depending on how far their leads are spaced, you can use different ones of the 3 different choices, but you basically just have a capacitor from here to here, and that's the capacitor under test. So we know from the previous example that this is the amplifier where we're converting the capacitance into a voltage, and instead of this little variable resistor I showed there, in fact that this is a similar resistor divider to what we would have for the voltage, but it's not the same resistor divider. 900K, 90K, 9K, 900 ohms, 100 ohms, adding up to 1 mega ohm for the whole thing. And you've got taps coming off on the range switches for 2 nanofarads, 20 nanofarads, 200 nanofarads, 2 microfarads, and 20 microfarads. So some combination of those resistors are connected as the feedback resistor, thereby changing the gain of this circuit, and it's acting on the 300 hertz sine wave and the capacitance of this, and that all determines what amplitude of AC signals coming out of here. And then once again we want to make sure that we're only looking at the 300 hertz component, not some other component that's got in there by accident. So here's our active filter. This is again a totally textbook circuit. They didn't do anything original or clever here. You've got a resistive feedback path with a capacitor to the input signal, and you've got a capacitive feedback path with a resistor to ground, and then you're feeding it with this signal, and basically what comes out of here is strictly the 300 hertz signal at an amplitude that's proportional to the capacitance. And you run it into that AC-DC converter we talked about already, and it takes that 300 hertz signal and converts it to a DC voltage that's proportional to the capacitance. We once again have that insignificant pair of resistors, and it comes in here and it's treated as a 0 to 200 millivolt signal. It is DC, and it's got to be in that range. Now the reference voltage here, again, it's done just like it is on the other simpler modes. You've got the DC cal voltage tapped off of the VDD and applied to the reference high, and the reference low is just connected to circuit common. So that's all there is there. Converting capacitive reactance to voltage and then measuring that voltage, and thereby knowing the capacitance. Okay, last one of my sketches. We're nearly done. So the meter can measure the HFE, or current gain, of a bipolar transistor. And it works pretty simply. It's just applying a voltage through a resistor to the base of a transistor, and the transistor is connected as a simple amplifier, and you end up with a current coming out of the transistor and into a shunt, and depending on what the current is, a voltage is developed across the shunt, and then we measure that voltage. So if, and we again have these jacks on the front panel. If it's a NPN, you use the 3 jacks for the NPN transistor, emitter, base, collector. If it's a PNP, you use the other 3 holes for the PNP, emitter, base, collector. If it's an NPN, you've got the VDD connected to the collector and through a 220 ohm resistor to the base, and then whatever current is coming out of the well, that causes a certain amount of base current to flow, and then depending on the current gain of the transistor, or the HFE of the transistor, you have a certain amount of current coming out of here, which is representative of the HFE. And then if we just flip the polarity around, if it's a PNP transistor, we reverse the emitter and the collector, and the base is tied low instead of high. The current goes the other direction, but it works out the same way. You still have a current going through here, which is based on the current gain of the transistor. Either way, you have current going through here, and it goes to this shunt. It's the same resistors that are used as part of the shunt for amps measurements, so it's doing double duty here. You basically have a 10 ohm resistor here, and the emitter current, or the collector current, runs through that 10 ohm resistor and develops a voltage across it, and then that voltage is measured through the top resistor in this shunt, a 990 ohm resistor going through a switch which is only closed in the HFE mode. And once again, you've got these resistors, but they're not very important, and it goes in here as a 0 to 200 millivolt signal into the input of the 7106. And once again, the reference input is just tied to circuit common, and it's based on the DC cal, just like a bunch of other modes. So very simple circuit. It doesn't take certain subtleties into account, so it's not a great transistor tester, but it will at least let you know what the HFE is approximately. It doesn't really have the functionality to do a thorough test, and it doesn't help you identify which leads are which. You have to know that already. But, you know, for a little throwaway feature they could add to the meter and make it look more attractive to buyers, there it is.